Hello students, today's topic is fixed beams. In this picture you can see this is a beam which is actually fixed into the walls. These are the fixed moments couples, and this is actual applied load. So in today's topic we are going to uh, know about how to calculate these fixed end moments, and how to draw the bending moment diagram and shear force diagram, and how to calculate slope and deflection values at any point on the along the length of the beam. So what is a fixed beam? Fixed beam which is built in, it supports, and slope at the end is always zero. In fact, deflection at the ends is also zero, and this is also called built-in beam or encaster beam or constraint beam. And here fixed end movements are developed at the both of the ends. It may be equal or unequal based on the load applied. If the loading is symmetrical, then at the both of the ends you will get equal fixed end movements, or otherwise if the loading is unsymmetrical, then you will be having two different values of fixed end moments. Right here, fixed end, these movements will try to hold back the deflection of the beam, and these fixed end moments will try to bring back deflection and maintain slope at the fixed ends zero. And particularly in this diagram you can see this is actually a physical fixed beam, and this can be, with a free body diagram, it can be shown like this. These are the various loads W1, W2, W3 and W4 at various distances. These are the fixed ends. Now this beam can be split into two parts: a simply supported beam of same length and same loading, plus a simply supported beam of the same length applied with the fixed end moments MA and ME. When you add these two, it will be equal to the effect of fixed beam. So that is idea. We can also place this fixed beam like a cantilever beam with a moment at the free end. That is also another option. Right. What are the advantages of fixed beam? Why we have to go for the fixed beam? So here the slope at the supports is zero, as well as deflection of the beam at its center considerably reduced when compared to the simply supported beam of same loading and same span. And even maximum bending moment induced at the center is also reduced because of the fixed moments developed at the supports. We have discussed these fixed moments will try to reduce or bring back its position, thereby reduce uh, bending moment in the center. And this beam is stronger and stiffer, and therefore makes more stable. Here the stiffness is the inverse of a deflection, therefore deflection is reduced because of the fixed ends again. But it has some disadvantages also. A little sinking of one support sets in the large stresses. Let us say if one of the this is a fixed beam, and if one of the support sinks, let us say right side support is sink by this much amount, let us say some small delta be the sink dimension, let us say delta deflection, then automatically with the effect of this sinking, additional moments are generated within the beam. Okay, so if one of the support sets, there will be a huge stress formation without any kind of loading, only because of this sinking only. Then the next point is temperature changes induce large stresses, right? In the simply supported beam, one of the support is used to have a hinged end, and the other we used to have a roller support, wherein that roller support will not have any lateral fixity. It will allow expansion, free expansion. What happens when the temperature rises in any material? it will try to expand based on its coefficient of thermal expansion proportional to its coefficient of thermal expansion as delta L is equal to L alpha T, right. So here in the fixed beam, both ends are firmly fixed and there will not be any change allowed. Therefore, with the rise of temperature, internal stresses are induced in the beam as movement is not allowed. And extra care is to be taken in align the support at the same level, right. So here skilled supervision is required and extra care is to be taken to align with the supports at the same level. What happens if the supports are not maintained at the same level? Obviously, this kind of sinking of support may happen, and thereby which results in the internal stresses or movements, additional movements, unknowingly without any loading on the beam. And frequent changes in loading, especially in case of moving load, make some degree of fixity at the supports uncertain. And this is also another disadvantage. But the above disadvantages can be prevented by providing double cantilevers. That means hinged joints are provided at the joint of points of contraflexion, right? Right. So here in the fixed beam, you will get 2 points of contraflexion. We'll going to see next diagram, bending moment diagram. We are going to have 2 points of contraflexions, wherein exactly bending moment is 0, and there you can put additional hinged joints. Thereby, these disadvantages discussed earlier can be eliminated. Since bending moment not having any magnitude at the point of contraflexion, hinges have not resist any moment. And bending moment diagram and deflection curve of the beam will be the same as for the fixed beam. It will not change with the addition of these hinge joints. Due to these hinges, variation in the temperature and small differences in the levels of support will not affect the bending moment. Yeah. Next, we are going to discuss about fixed end moments. What is this fixed end moments? Due to fixity of both ends, the resisting moment will be developed based on the loading at the both ends. This actually responsible for making zero deflection and zero slope and minimizing the overall deflection even at the center. If the simply supported beam AB carrying an external load, and it will be subject to bending, and thereby slopes at A and B will occur at the fixed ends A and B. If these slopes are to be arrested or prevented or stopped, it is necessary to apply some couples, end couples, and the ends are built in and movements automatically develop. These movements are called fixed movements or fixed end movements or support movements. Next, we have how to analyze a fixed beam. We have fixed beam carrying point loads at its center, and fixed beam carrying UDL on entire span. And we will also discuss fixed beams carrying eccentric loads also. Yeah, we have covered what is mean by fixed beam. A beam which is fixed at both ends or firmly built in at both ends is called fixed beam. And statically, fixed beam is a statically indeterminate beam. It is not determined because additional equations are required to calculate the unknown forces, unknown reactions. Yeah, we know statically determined beams are those in which unknown reactions can be determined by simply applying equilibrium equations, that is sigma h is equal to 0, sigma v is equal to 0, and sigma m is equal to 0. Whereas statically indeterminate beams are those in which additional equations are required to calculate all unknown forces apart from the equilibrium equations. And fixed beams, because of the both ends are fixed, at the each end of fixed you will get 3 unknown reactions. 3 plus 3 total put together 6, but you have only 3 equilibrium equations, that is sigma h is equal to 0, sigma v is equal to 0, and sigma m is equal to 0. So uh, total we have 6, 6 minus 3 is equal to C 3. Therefore, fixed beams is third degree uh, statically indeterminate. Right. So here in the fixed beams, the for analysis we need to calculate the fixed end moments. Once it is calculated, it is as good as a simply supported beam with the additional couples at the both ends. Therefore, main criteria here lies with the calculation of fixed end moments. So to calculate fixed end moments, we have different methods as listed here. The first one, moment area method, and double integration method. Second, method of superposition or flexibility method, and theorem of three moments method. And in this, we have in our syllabus we have moment area method, and we are going to discuss in detail in the first method only. Analysis of fixed beam using moment area method. Consider a fixed beam of length L carrying a pattern of loading as shown in figure. Let MA be the fixed end moment at support A and MB be the fixed end moment at support B. And bending moment diagram for the given loading is drawn. And if the beam had been a simply supported beam, let the area of the bending moment diagram be mu, and CG of Bending diagram is some at x bar from support A. Here you can see the diagram. Yeah, this is the diagram. Fixed beam with some kind of loading. It may be a UDL or a point load generally. Let us say some kind of loading is applied on this fixed beam, and this is the bending moment diagram drawn treating this fixed beam as a simply supported beam with the same given loading. Okay, and let us say this is the center of gravity of the given bending moment diagram with respect to A, x bar be the distance of centroid. And now fixed end moments are generated MA and MB. These this is actually fixed end moment diagram, a simply supported beam with only couples, that is fixed moments applied at MA and MB without any kind of other load. If you draw the bending moment diagram, it will be like this. But for the fixed beam, it is a combination of these two. That means when you superimpose these two bending moment diagrams, you will get this type of a bending moment diagram. This is the bending moment diagram for the actual fixed beam. So here at the center you will get a sagging bending moment, and at the supports you will get a hogging bending moment. Yes. In figure shows bending moment diagram for the beam considering only fixed end moments MA and MB as we discussed now. Yeah, these are the four diagrams: fixed beam, bending moment diagram for carrying simply supported condition, fixed end moment diagram, and bending moment diagram, fixed beam. Yeah, these are the four different diagrams. Let the area of fixed end moment diagram be mu dash, and the distance from its CG from measured from A be some x bar dash, like this. This is for the fixed end moment diagram. Now, moment due to given loading causes sagging, and it is taken positive, while fixed end moment causes hogging bending moment, and it is considered as negative. And by superimposing both B and C, the bending moment diagram for the fixed beam can be obtained as shown in figure. And now, according to the first moment area theorem, what is the first moment area of theorem? Slope between any 2 points is given by area of the bending moment diagram between those selected points divided by flexural rigidity EI will give you slope between those 2 points. Right. According to the first moment area theorem, the change in the slope between A and B is equal to the area of M by A diagram between A and B. And for a uniform beam, that means with a uniform cross-section area, EA constant for entire span of the beam, and hence the change in the slope A and B is equal to the area of the bending moment diagram. But due to end fixity, the slope at the both ends remains zero, and therefore change in the slope between A and B is considered as 0. So that means area of these two diagrams divided by A will also be equal to 0. Hence the area of bending diagram between A and B should be equal to 0. That means magnitude of both positive bending moment is equal to the magnitude of negative bending moment or fixed moment diagram. That means mu must be equal to mu dash. Yeah, let us write equations for mu dash. This is mu dash is related to fixed moments. I'll go back. A fixed moment. This is nothing but a trapezoidal one. So for a trapezoidal, we know the formula MA plus MB divided by 2 into L. Right. So half into A plus B. Average of these two into length will give you area, and this is equal to actually mu. So mu is equal to MA plus MB divided by 2 into L. So here you will get one equation. When you equate this MA plus MB equal to 2 mu by L, this is one equation. And according to the second moment area theorem, the intercept made by the tangent to the elastic curve at A and B on a vertical line through A should be equal to the moment of the M by A diagram about A. So here moment area theorem we must have discussed in the topic of deflection of beams. So here this is actually for deflection. I'll try to explain again. Let us say this is a simply supported beam. Yeah, this is one support and this is another one. With some kind of loading, if you apply load, let us say this is a deflected profile or elastic curve, then we are considering two tangents. Let us say this is one tangent to elastic curve and this is another tangent to the elastic curve. These are the two tangents, and now we need to consider a vertical line. Let us say I am considering vertical line exactly at the support. Now intercept made by these two tangents on this vertical line is nothing but the Maxent deflection in this case. So similarly here, and this value intercept is also equal to the deflection, and that is given by moment of the M by A diagram between those selected 2 points, right? So here we are selecting 2 points at the both ends EA and B. Right. When EA is constant, this will be equal to the moment of bending diagram about A. Since the tangents to the elastic curve at A and B coincides at the supports A and B are the same level, and the intercept of two tangents on vertical through A shall be equal to 0. That means for a fixed beam, if you draw a deflection diagram, it will be hogging up to certain point. It will not deflect up to certain point, and then it will be straight up to here, and then it will try to uh, sagging, and again it's hogging. So that means if you draw tangent, it will be exactly coinciding with the initial line, and similarly if you draw tangent on the other side also, it will exactly coincide with the initial line. These two will merge, and therefore if you consider a vertical line on the right or left, no intercept will be made. That means intercept will be exactly equal to 0, and the same thing applied here. Mu multiplied by x bar will be equal to 0. Yeah, we don't know the value of mu as well as x bar unless we draw the bending moment diagram for the simply supported case. But here mu dash and x bar dash can be calculated, right? Yeah. So, yeah, and we know from the equation 1 mu is equal to mu dash, isn't it? So earlier, yeah, mu is equal to mu dash. So from this, when you equate here, x bar must be equal to x bar dash, right? Thus, for a fixed beam with the end supports at the same level, x bar must be equal to x bar dash, and the distance of centroid of bending moment diagram for any end, from any end in the simply supported beam end condition is the same as distance of centroid of fixed end diagram from the same end. Yeah, but here x bar dash can be calculated from the fixed end diagram and made equal to 0. And yeah, for this diagram, I'll show you. So for this diagram, we'll try to find out the centroid. Okay, for a trapezium. So it is L by 3 multiplied by MA plus 2MB plus MA plus MB, and therefore mu x bar is equal to mu dash into x bar dash, right? When you simplify, finally we will get MA plus 2MB is equal to L square by 6, or MA plus 2MB is equal to 6 mu x bar by L square. Right, this is another equation, and earlier we have one equation from this ma plus mb is equal to mu into l by 2 mu by l. This is one equation, and this is another equation. We have two equations and two unknowns, that is ma and mb. Other values mu or x bar or l are the known values, and by simplifying these two equations you can calculate the support condition, support moments. So this is a basic theory of calculating any uh, fixed end moments of for any kind of loading. And here we are going with the first case, that is a simply supported beam carries central point load. Okay, where is the diagram? Yeah, I'll try to draw the diagram over here. Yeah, this is a fixed beam with the central point load of say some W over here. Yeah, consider a fixed beam AB, like this AB, fixed at A and B, carrying a point load, and W at its midspan. That means this is L by 2, and similarly L by 2 over other hand. A, B, and L by 2 on both the sides. L by 2 and L by 2, right. Let the fixed end moment at A, B, MA, and fixed end moment at B is MB. Since the beam is symmetrical, MA and MB both are equal, and the mu diagram, this is actually mu, the mu diagram will be a triangle, and mu dash diagram will be a rectangle. You know, mu diagram is nothing but for the same condition, for the same beam, you treating these both ends as a simply supported, you need to draw the bending moment diagram. So for this central point load, we used to have a triangular bending moment diagram with the central maximum value of bending moment as WL by 4. And similarly, for a fixed beam, fixed end moments MA and MB, with those two values, you will be having a trapezium. But as loading is symmetrical, both of these fixed moments will have same value M and M. Therefore, fixed end moment diagram will be a rectangle. And now, first condition based on moment area first theorem, equating areas of the two diagrams, MA into L, nothing but half into L into WL by 4. This is a triangular area, half into L into WL by 4, and this is rectangle fixed end moments area. Yeah, you can write here MA or MB, both are equal, or simply M also. And from here, when you simplify, you will get fixed end moments as W, sorry, so it is actually, yeah, MA into L is equal to WL square by 8, and when you calculate only MA, it is WL by 8. MA and even MB also, both are equal in magnitude but opposite in direction. And the bending moment diagram under simply supported condition is WL by 4. maximum at the center, and bending moment at midspan, let us calculate. So at the midspan, with the simply supported condition, you will be having WL by 4, and with fixed end moments WL by 8. So net value of WL by 8 you will get at the center. And bending moment diagram fixed for the fixed beam you can draw. And for calculating reactions, now having known the fixed end moments, you can now calculate the support reactions. Equating moments about A, RB into L plus MA is equal to MB plus WL by 2, and from this when you simplify, MA and MB both are equal, gets cancelled. RB into L over here and L over here gets cancelled, simply W by 2, and therefore by symmetry other load is also W by 2. With this you can draw the shear force diagram. And now to find the to find the slope and deflection for the fixed beam carrying central point load. Now because of the symmetry, point of contraflexion occurs at a distance of 1/4 from both ends of the beam, and bending moment at any section is mx is given by w into x by 2 minus m, that is wl by 8. Here we'll use a double integration method or Michaelis method. Differential equation of bending EI d square y by dx square is equal to m, wherein we'll substitute this m over here, and we'll integrate the equation once, and thereby you will get EI dy by dx is equal to w by 2 taken out and x integration x square by 2 plus some integration constant c, and again wl by 8 is a constant multiplied by x, and this is C1 over here. And to find the C1, let us substitute the boundary conditions. What are the boundary conditions? Dy by dx is nothing but slope. We know for a fixed beam at both ends will have a zero slope. Therefore, at x is equal to 0, that means x is equal to exactly at the support, slope is also 0. You can substitute these two values. When you substitute dy by dx is equal to 0 multiplied by EA, everything will be equal to 0 on left side. Similarly on the right side, x value is 0, therefore here also in this term you will have some x value, and here also x value, both these terms will be 0. Finally we left over with the C1, therefore C1 is now 0. And integrating the same equation once again, you will get EIY is equal to W x cube by 4 into 3 and WL x square by 8 into 2 plus C2, as C1 is equal to 0, we already got. And again applying boundary conditions to calculate the C2, and here we also know at both of the supports, apart from the slope, deflection is also 0. That means at x is equal to 0, y is equal to 0, and this condition you can apply over here, and y is 0, therefore entire thing on left side is 0, and we have three terms apart from and in every term we have x value, and this will be 0, this will be 0, finally C2 will be equal to 0. And now you have two equations with the known values, and here EIY is nothing but a deflection equation, EI dy by dx is nothing but slope equation, and with the all C1 and C2 values, now this equation is ready. You can substitute the x value anywhere, and then and by substituting that value you will get deflection at the particular point. Yeah, this is the required equation for deflection at any section. Maximum deflection occurs exactly at the midspan. Because of the symmetry, you will get directly. Otherwise, always occurs at a point where slope is 0. Apart from the support, at the point of maximum deflection, slope is always 0. Right? So now, because of the symmetry, we can directly know At x is equal to L by 2, you will get uh, L by 2 will get maximum deflection, and simply substitute x is equal to L by 2 in the above equation. W into 4 by 3, that is 12, and x cube, but here x you need to substitute L by 2, not 1 by 2, L by 2, so L by 2 whole cube, and again WL by 8 into 2, that is 16, taken out, and L by 2 whole square. And finally, by simplifying, you will get WL cube by 192 as a maximum deflection at the center for a fixed beam carrying central point load. And here negative sign indicates deflection is downwards. So like this, you can calculate the maximum deflection as well as fixed end moments. Fixed end moments for the fixed beam carrying central point load. So with this, we have completed today's topic, and let us go to the first. Yeah. Yeah, we have discussed about definition of fixed beam and what are the other names of fixed beams. And this is a typical diagram with the physical meaning, and this is free body diagram, and it can be split into two parts, as I said, a simply supported beam with a given loading as well as a simply supported with the fixed end moments, and when you add these two you will get the final effect that is of a fixed beam. And it has advantages over simply supported beam, such as bending moment is reduced much when compared to the simply supported ends, and deflection is also reduced, slope is zero, but it has some disadvantages, and these disadvantages can be overcome with the introduction of hinges at the point of contact flexures. And we have discussed about what is the fixed end moment, and how uh, this is creating or reducing deflection or making slope zero. And yeah, we have discussed the first case, simply supported a beam carrying central point load. And we have also discussed about statically determined beams and statically indeterminate beams. And here I want to tell you in the moment area method how to calculate center of gravity of this trapezoidal shape. Here formula directly given like this: x bar dash is equal to L by 3 into MA plus 2 MB by MA plus MB, or otherwise we can also split this diagram into two triangles like this. Two triangles with MA into L over here, similarly MB into L on the other side. And if you draw, if you write the equation x bar dash, I will say x bar dash is equal to, for the first diagram I will write the area half into what is called MA multiplied by L. This is actually area, multiply by, let us say, distance from A. Because it is a triangle with the base at A, therefore I will get L by 3 only. L by 3, and plus the second part, again it's a triangle with the base on right side, therefore area of the triangle again half into, I'll write MB yeah, multiplied by, now distance to the center of this triangle will be 2L by, I'll write 2L by 3, okay, divided by area of the two diagrams, that is half into MA uh, plus MB into L. right? So like this also you can calculate, and when you simplify this, you will get the same equation as over here. Yeah, L by 3 into MA plus 2MB by MA plus MB. Let us check now. Yeah, you can take out common values by L by 2, L by 2, L by 2 on all sides gets cancelled, and here L over here and here gets cancelled. Here also actually L should be there, area half into MB into L. So we left over with a common value L by 3. You can take common, multiply by MA over here, isn't it? MA over here plus 2 times MB. So 2 MB over here divided by MA plus MB. Simply over here MA plus MB. I think the same equation. Yes, we have the same equation just like this. Yeah, if you don't remember direct value, you can always derive or calculate with the basics. Like this trapezium is now divided into two parts, like this with MA plus another triangle with the MB. Okay, so this is MA, and here it is MB. Length same in both the cases, that is L. Okay, now you can see the first diagram, area half into area of this triangle half into MA into L. Up to here it is area, and L by 3 is the distance from end A, from here to this centroid. This distance is L by 3, whereas the second part centroid will be at 2L by 3 with respect to A, therefore it is 2L by 3 now. Again half into MB into L is nothing but area, right? So like this you can calculate the uh, equation, right? Yeah, we have discussing about moment area method. So in this moment area method, using this moment, we have also other methods for calculating fixed end moments. Moment area method, double integration method, method of superposition or flexibility method, and theorem of three moments. This theorem of three moments, anyhow we are going to discuss in continuous beams also. And now we have only moment area method for analyzing fixed beams in our syllabus. So let us continue with that. Yeah. So here theory lies, the fixed beam is now divided into two parts. One, simply sorted beam with the bending moment diagram for the given loading can be drawn first, and other, the same fixed beam with the removal of loading and application of only simply fixed end moments is drawn, and then by calculating based on the moment area theorem 1 and theorem 2, that is m by ea diagram should be equal to 0, and m x bar by ea diagram should be equal to 0 for the combination of these two diagrams. By applying those two equations, you will get sorry two principles, you will get two equations in the form of MA and MB, and uh, and also in the form of some mu and L, where mu is the area of bending moment diagram and x bar is a centroid distance of bending moment diagram. So with the known values mu and x bar, you can calculate the unknown reactions MA and MB for the above two cases. Uh, yeah. So here this is the first equation, MA plus MB is equal to 2 mu by L, and based on the second moment area, that is M by EI, moment of M by EI diagram. With this you will get MA plus 2MB is equal to 6 into mu into x bar by L square. In the both of these equations, mu, x bar and L and these can always be determined, so that two equations, two unknowns mb and mb can be calculated. And we have also taken a first case, a fixed beam carrying central point load with fixed end moments at A and B, central point load W, length L, and we have also drawn shear force and minimum diagram for the beam. And this is about slope and deflection. So here what we have done with the help of double integration method or Michaelis method, we have seen, yeah, this is a differential equation of bending. Ei d square y by dx square is equal to m, where m is a continuous expression for movement anywhere in the beam. And here what we are going to do, integrate once this equation, and thereby you will get dy by dx and integration constant c1. And similarly again we are going to integrate this equation. Now you will get EIY is equal to equation with the C1 x and C2, and this C1 and C2 are the integration constant that can be eliminated by applying boundary conditions, like at x is equal to 0 dy by dx is 0, and at x is equal to 0 y is equal to 0. And upon applying these two boundary conditions, you will be getting that integration constant C1 and C2, and thereby when you substitute or eliminate these two constants, we'll left over with the direct equation without any integration constants in the form of uh, EIY or EI dy by dx. Now this EIY equation is nothing but deflection equation for anywhere within the beam. uh, yeah. Now, in order to calculate the maximum deflection, you have to know a point where maximum bending moment, maximum deflection occurs. But having this is a symmetrical case. For a symmetrical loading case, you will always get maximum deflection at the center. Therefore, simply L by 2 is equal to x. You can substitute in the above equation, and when you simplify, you will directly get WL cube by 192, and EI will come to over here. Finally, y max or deflection max is equal to WL cube by 192 EI, where this minus sign indicates downward deflection, as the loading is always downward. So I think with this today's class is over. I hope this lesson is useful to you, and we'll looking forward to that. In the next class we're going to discuss about a simply supported beam with the UDL case, and we are also going to solve some problems for the case discussed today, that is a fixed beam carrying a central point load for the various load cases. Okay, thank you all.